Oh, well, hello, friends. How are we all today? All right. We started last time talking about exponents, and today we're going to take that idea of exponents into its inverse operation, which is logarithms. So, logarithm, it's a fancy word, but a lot of times we just use the prefix. Instead of logarithm, we use the prefix log. It's this idea that we can go back and forth to help ourselves be able to get things into more usable areas. Sometimes we end up with some sort of problem like 3 to the y equals x. And if we're trying to graph it, well, we need to have y by itself. So because of that, then we end up using what we call this definition, where we can actually change the form of something. So whatever the base is, we can change it from exponential form to log form. So whatever the base is, that would become the base over here. And we can switch then our x and our y. All right, so it's a way to get y by itself so we can graph it. So we have some common logs that you guys probably learned a little bit in Algebra 2 or Integrated 1, where it says no matter what the log is, no matter what the base of the log is, if you're taking the log of 1, that always equals 0. And the reason for that is, remember, if we want to go from log form to exponent form, the base would stay the base. The base of 3 would become the base of the exponent, and then the numbers switch sides. So 3 to the 0 equals 1. Likewise, no matter what the log is, what the base of the log is, if the base equals the number, then that equals 1. So I don't know why we use that. I meant to use 3. There we go. So log base of 3 would be equal to 1. And again, no matter what the base is, the base stays the same when I switch to exponential form. Exponential log, everything stays the same. The only thing that changes is instead of having the 3 with the base, now I'm going to have the 1 with the base when I switch to the other form. So 3 to the 1 equals 3. This idea, which is true, this idea of switching back and forth between log form and exponential form, that's called the definition of a log. Now we have a couple logs that mean a lot to us, that are what we call the most used logs. We have log where there is no base, and if there is no base, we assume the base is 10. So you'll find that one on your graphing calculator on the left-hand side. You'll see just a regular thing that says log. And if you notice above it, you'll have the 10 to the x button, because again, an exponent with base 10 is the inverse of a log of base 10. This ln, that's called the natural log. It's actually Latin. It's like logarithmic de naturale. But and what ln means is that should technically be a log right there. Log base e. ln is basically a log base e. And remember what e stands for. E is that Euler number, right? And we kind of looked at that one before last time, where E is the number 2.7182818283. That's called the Euler number. So this idea of I should have made that. There we go. Of the Euler number is the log that is natural. Remember, this E is used in exponential growth. We use it in compound inequalities. Last one. All right. This is a really big log for us. Okay. This is the log we use most often when you get to calculus. So you'll find out this one also on your calculator. And we talked a little bit about where this exponent button is, this E exponent button is. And you'll find it right there. And again, it's on the left-hand side of your calculator. It's right underneath the log button. So on the left-hand side of your graphing calculator, right underneath the log button. So we have the natural log and the common log. Those are the two biggest logs that we have, and the ones that make the most sense to us. So there are a few things that are so important that you need to remember. You cannot ever no matter what the base, you can never take the log of a natural number, of a negative number. We never, ever take the log of a negative number. Friends, when that happens, if you're ever taking the log of a negative number, you just tell yourself that log does not work. Cannot take the log of a negative number. Likewise, I don't like how that is written right there. You can never have the log of base 0, and you can never have a log where the base is a negative number. These also are no good. Can't take a log of base 0, can't take the log of a negative number. All right, these right here, bad, cannot do it. You also really should never take the log of base 1, but that's another story. It's not a big deal. But can't take the log of 0, can't take the log of a negative number, or can't have a log of base 0, can't have a log of a base of a negative number, and you can never take the log of a negative number. And if you remember back, the reason why you can't do that, if you go back to where we actually talked first semester, when we just looked at some family graphs, we actually looked at the log graphs. And if you remember, we had a vertical asymptote for our log graphs, and the graph looked like this. That vertical asymptote never allowed us to cross the y-axis because you can't take the log of 0 and you can't take the log of a negative number. So you got to remember, cannot take the log of a negative number, cannot take the log of 0. 0 cannot be your base. Negative numbers can also not be your base. So all we're going to do today is we're not going to go crazy today. We're just going to go back and just review this idea of simplifying logs. All right. And there's a couple of different ways to do it. I'll show you the way we're going to do it today, but I'm also going to show you a shortcut way that we're going to be doing it next class. So log base 5 of 25. We're going to evaluate these without using a calculator. So if you ever want to find a base, all you do is you just take it and set it equal to a variable. So 5, pick a variable, doesn't matter, 5 to the x. And we're going to switch from log form to exponential form. So whatever the base is, remember that the base will always be the base. So the base of 5. And then my number in my variable, we're going to switch. So instead of 25 with the base, when I switch to exponential form, the x goes with the base. So 5 to the x equals 25. So 5 to the x equals 5 squared. X, that's a horrible looking x there. X equals 2. So that means log base 5 of 25 would be equal to 2. Now, next class, we're going to actually learn a little bit. Our next lesson, we're going to learn a little bit quicker way to do it. I'm going to show you briefly what it is, just to kind of give you an idea on it. Another way to look at logs, if you want to simplify them, so if you want to do this today, you can, is another way is we can make use of the exponent right from the very beginning. If I look at 25, and this one is kind of cool because I don't have to switch to exponential form. So 25 is the same thing as 5 squared. So the next class, we're going to talk about 3 different log rules. And one of those is this exponential rule. And it says if you're taking the log and it has an exponent, that exponent can come in front. So the 2 can actually come in front and be the same thing. So this is the other way to go about simplifying those. So we still have base 5 of 5. And like we said earlier, anytime the base and the number are the exact same, that is going to be equal to, anytime the base and the number are the exact same, that equals 1. So 2 times 1 would be 2. So again, 2 different ways to go about doing it. One of them, you can set your log equal to a variable and change to exponential form. Or the other one is you can use it and play with this idea of exponents. But for today's purposes, I'm going to stick with exponential form. So log, let's try this next one here. Log base 36 of 6. So I'm going to set it equal to a variable. My base will stay my base. So 36 stays my base. But now when I go to exponential form, the variable and the number switch. Now I make them have the same base. So 36 is the same thing as 6 squared. So 2 raised to the x is 2 to the x. And this 6 right here would have an exponent of 1. So we have 2x equals 1. X is 1/2. So that means that log base 36 of 6 is actually equal to 1/2. This is equal to 2. All right, let's try this one. Log base 7 of 1/7. So I'm going to go ahead, just like we did before. I'm going to set it equal to a variable. And remember that the base is always the base. So 7 to the x equals 1/7. In order to get that 7 out of the denominator, I got to go back and remember that there's actually a 1 here. And so I can think of this as a negative exponent. So if I want to get it out of the denominator, I can take that 1 and make it a -1. So now it's out of the denominator, which means that x then is equal to -1. All right, why don't you guys go ahead and pause the video and then try problems 4 and 5. All right, and then we'll come back and talk about it. All right, so 4 and 5, let's see how we did. All right, so I'm going to set this equal to x. And again, you're going to hear this a lot. The base is going to stay the base. So 8 to the x equals 4. Now, there is no way to turn 4 into a base of 8 or 8 into a base of 4. So I got to pick a different number to make them have the same base. Well, they are both powers of 2. So I'll try that. 2 to the x equals 2 squared. So we have 2 to the 3x equals 2 squared. So 3x equals 2. And x is 2/3. So that means this log right here is equal to 2/3. You can try it again with the other one now. Log base 25 of 125 equals x. The base will always be the base. And then I switch the variable and the number. So again, I'm looking at this. I'm trying to figure out some way to find a base that will make them have a common base. So we're going to make them, they both are a base of 5. So 5 to the 2x equals 5 to the 3. So I have an exponent raised to an exponent. So I'm going to multiply 5 to the 2x equals 5 to the 3. Now they have the same base. I can get rid of the bases and set the exponents equal to each other. So 2x equals 3, x equals 3/2. All right. Why don't you guys do me a huge favor here? We're going to play a little bit more now. Go ahead and pause the video and try 6, 7, and 8. Pause the video, try 6, 7, and 8. All right, let's see how you guys did. All right, so we have log base 3 of 127. We're going to set it equal to a variable. So the base is always going to be the base. So 3 to the x equals 1 over 27. Well, 27 can be the same thing as 3 to the 3rd. So we can go ahead and try that real quick. And then to get it out of the denominator, I make it equal to a negative value. So instead of 3 to the third, that can become 3 to the negative third. That means x equals negative 3. Okay. Log base 17. I don't know about you. I don't count my 17s real well. Luckily, I noticed something here. Log base 17 of 17. Well, friends, turns out the bases are equal. The base is the number. So if I'm taking the log base 17 of the number where the bases are the same, that just equals 1. There's nothing to solve there. That was one of our rules. That equals 1. Let's see here. Our next one we have is log base pi. I'm not gonna lie, I don't count by pi real well. Log base pi of 1. And again, that was also one of our rules. Anytime I'm taking the log of 1, I don't care what the base is, as long as it's a positive number, whatever the base is, that means it's equal to 0. All right. That's not too bad. Let's keep going here just a little bit more. Friends, why don't you go ahead and see what you can do with number 9 and number 10. All right, let's see how you did, friends. So remember that we have log of 1,000. So before I do anything here, I remember something about this. If there is no base there, that means it is my common log. So it has a log of base 10. So I'm going to set that equal to a variable. All right, so we have 10 to the x, because whatever the base is, it's still the base, and the variable and the number change sides. So 10 to the x is 1,000. That means 10 to the x equals 10 to the third. So that means x equals 3. Let's try this next one here. We got log of 1 over 10,000. Whoa, in the world. All righty. And if we're missing a base, we're going to go ahead and make, again, that means that this is the common log. So we're going to add in our common log base here. Make that equal to x. So even though we can do this on our calculator, we're approaching these as if we can't do them on our calculator. So we should be able to simplify some of these logs without using a calculator. All right, so we have 1 over 10,000. So that means 10 to the x equals 1 over 10 to the 4. 10 4, good buddy. Over and out. All right, and then make that exponent positive. Since it's a positive, I can get it out of the denominator by making that exponent negative. So that means x equals a negative 4. That means this is equal to negative 4. So we can solve problems that involve common logs, just like we can also solve problems that are the natural log. Those are the ones that are e. So go ahead and pause the video and see what you can do with numbers 11 and 12. We'll come back and take a look at them. All right, friends, 11 and 12, our last two of the day. So we have natural log of 1 over e. So right now, whenever you see natural log, remember what that actually refers to. That refers to log base e of 1 over e. And again, e is just that natural number, that Euler number. So we're going to treat it like pi. We're going to treat it like I. We don't do anything with it. We just leave it as e. Leave it like a variable. So we'll set this equal to it. We'll set this equal to an exponent, or a variable, I'm sorry. And now this e right here, the base always becomes my base. So e to the x all over 1 over e. So remember that this e right here, if there is no exponent, we assume it's 1. So I can get that e out of the denominator by making it e to the negative 1. So that means x equals negative 1. That means this equals negative 1. All right, let's try another one here. Natural log of the square root of e. All righty, well, that's kind of neat. Better. All right. Well, first of all, friends, I don't know about you, but this idea of a square root, not a big fan of, but I remember that square root is the same thing as an exponent. So that's e to the 1/2. So now that means that this is going to be log base e to the 1/2. Okay, so we'll set it equal to a variable. Don't care what, I'll call it x. And remember that the base of the log is going to be the base of my exponential. So e to the x equals e to the 1/2. So that means x equals 1/2. All right. So friends, we spent last class looking at how to simplify exponents, or just reviewing them actually. And today is just a day of just reviewing how to simplify logs without using our calculators. So the next couple of days is when we're actually going to get into this idea of operations with logs, solving equations with logs, and get that log practice that we need. All righty. Folks, have a wonderful, wonderful evening, and I will see you tomorrow in class. Take care.